Hello. How is everyone doing today?
Hi, Peter.
Hey, Alex.
So do we know like when the session actually starts? Like will it show on the screen? I'm, I mean, I'm
Uh,
assuming it will.
yeah, I think on the schedule it's 3:30 to 4:50 maybe.
Yeah,
Oh, no, sorry, 3:50, right?
yeah.
Hey, good morning, everyone. Or good afternoon.
Hi, Piro.
Hey.
So
Okay, 3:30.
let's just start early.
So
No, I'm kidding.
we start right at 3:30, I'm assuming.
Yeah.
Yeah. So I think we have Palav, who's already a fan, hopefully, in the chat. That's cool. Hopin also says your internet connection for you guys. You guys are at 2 bars.
I've used Hopin for many different things, right? Because BDO uses Hopin as well.
Yeah.
And I won't say what my personal opinion is.
Okay, I maybe we'll get to hear that more on Monday then. But have you guys watched any of the other sessions so far?
I have. I watched Rishan's keynote. He did really well.
Yeah, I saw some of that as well, and the one before them, the woman in tech as well. I
Yeah.
looked a bit on that one. Yeah. Should we start?
Yeah, well, I mean, we have 21 people, 22 already, so
Okay,
I
great.
think it's safe to say.
So, hi everyone. Welcome to the Data Science CodeAlong. We hope everyone's enjoying the conference so far. BDO is excited to present this session on data science, and we hope everyone's able to learn something, and maybe it will spark a career in data science for you. I would like to introduce your speakers for today. I am Alex Ng. I'm a senior manager within Technology Consulting and lead our data AI practice. With me today is Piro Dhimitri. He's our manager of data science, and he's going to be introducing us to the world of data science today. And Poydenko, who's an intern with us this term, and who will be leading us through this CodeAlong. BDO Canada is celebrating 100 years of helping people and organizations achieve their dreams. With over 4,100 employees coast to coast, and 600 of them part of our technology consulting, we are known as one of the premier data AI practices in Canada. BDO Consulting offers a full range of offerings to our clients, including management consulting, data, digital, cyber, and risk advisory. We deliver solutions in many different industries, from energy and natural resources to banks and insurance companies and the public sector. And so we have many different offerings to help all of our clients with whatever solutions they need. I'll now pass it to Piro, who's going to introduce us to data science.
So welcome, everybody. Thank you for the introduction, Alex. One of the key buzzwords in today's society has become artificial intelligence, and another one that usually is synonymous with it is machine learning. But what we really want to do today, and especially for the next couple of minutes, is identify what the difference between the two is, and when we should use machine learning and in what context, and when we should use artificial intelligence and in what context. So artificial intelligence is the act of trying to replicate human decision making. Sorry, Peter, can you please go back? Is the act of replicating human decision making in computers. And believe it or not, we've been actually able to replicate human decision making in computers since the 1970s. Some of our early computers had the powers to make decisions and kind of compute some of those early decisions for us. But the level of complexity in that was very, very weak. What we call that is deterministic intelligence. So this is rule-based intelligence. And some of you may know this as if this, then that type of decision-making, or case-based decision. So when this is the case, do something. When this is the case, do something. But what's happened recently, and especially since the late 2000s, is that we've seen a rise in the amount of computing power and memory that we've had available to us. So what we've been able to do is ingest more power, more data, and have the power to compute all of this. So we've been able to switch our approach from a deterministic approach and more rule-based approach to a more probabilistic approach. When we introduce probabilistic methods into our computing, what we're doing is we're introducing machine learning. Machine learning relies on having the computer have a set of historical data stored in memory that it can quickly recall, build an equation that defines what happened in history, and then eventually use that equation to predict what's going to happen in the future. So in this scenario, something as simple like a linear regression, or what you guys might know more familiarly as y equals mx plus b, is a form of machine learning. So we are applying a method into a probabilistic method to actually determine some sort of outcome. And what's happened is that in the last couple of years, we've had, with the rise of cloud computing, with the rise of computing power and memory and storage, we've actually been able to go a little bit deeper. So our first machine learning models were shallow learning models, where we would take one pass, create a model, and then eventually use that model to predict something. What we've been able to do recently is build what's known as deep learning models. So deep learning models rely on multiple passes of the data. In other words, correcting the errors that the first model could not account for. And what happens is if you make a mistake, there's a second net that is brought in to actually fix the mistakes of the first equation, and then you have another equation that fixes the mistakes of your previous equation, and so on and so forth. And ultimately what happens is you built a multi-layer model and that is what is labeled as deep learning. So when you hear some of these words and some of these acronyms and some of these concepts, you'll now be able to understand that artificial intelligence is something that we've had for a very long time. Machine learning is something that has been recently introduced, and our future lies in deep learning, where we can make multiple passes and fix the errors of our initial models. Next slide, Peter. What we're going to be doing today is talking about machine learning and the machine learning methods that are available to be used in industry, but also in science as well. There are two key types. There's supervised learning and unsupervised learning. In supervised learning, there's an outcome. There's already an outcome given to the computer. In other words, there's already a yes or no or a value that the computer is presented with. And what it's going to try to do is it's going to match that value for historicals. So in other words, it's going to look in that deep history bank and try to find the closest value that matches to those input variables. So there's two types of supervised learning problems. There's regression problems, and then there's also classification problems. Regression problems, like the linear regression I was talking about earlier, is one of the types. We also have logistic regressions, which are more for binary classification, 0 or 1. We also have decision trees, which are statistical in nature and try to predict an outcome that varies in domain and in range. We also have classification models. We have naive Bayes, we have support vector machines, and k-nearest neighbors. And what this tries to do is it tries to classify scenarios based on historical scenarios. So things like a banana versus a pear, looking at the curviness versus color, and then trying to understand, is it a pear or is it a banana, and then trying to classify things like that. We also have unsupervised learning, where a computer has to look at all the data as a whole and essentially try to pick apart which sets of data look most alike. So in unsupervised learning, there is no outcome. It's the job of the computer to actually determine the outcome. This is most likely used in clustering algorithms. So clustering algorithms usually try to identify like and unlike scenarios. So in other words, abnormal and normal scenarios. Clustering algorithms are especially useful when we're trying to identify fraud, specifically through banks and insurances, because what they try to do is they try to identify what is abnormal behavior and what is actually normal behavior. We also have dimensionality reduction. I won't go too deep into dimensionality reduction because it's a method that we use to kind of bring multiple variables into and represent them as ultimately one variable. In the other corner, we have reinforcement learning, and that's just a type of deep learning that we can go through without getting too deep into it. One of the questions that I see in the chat already is, how does machine learning relate to deep learning? Think of machine learning as the parent to deep learning and shallow learning. Shallow learning being that one pass and deep learning being that multi-pass approach. So what I'd like to do now is we're going to focus on one type of algorithm today, and that's under the regression column. We're going to be doing a decision tree algorithm, and Peter is going to be showing you guys how we can take a decision tree algorithm and a set of data that is actually a group of 70,000 pictures of various handwritten numbers. And what we're going to do is we're going to feed that into our computer, and the computer is going to be able to predict what number is shown in the image. And Peter's going to be showing you how to do that. So I'll let the coding begin. It's very, very simple. You can follow along by going to Google Colab. And if you have a Gmail account, a Google account, you can log in. And this is a resource that's available to you for free. You can code using your notebooks that Peter's going to show. And you can actually create notebooks and use some of the Google computing resources for absolutely free. So all you really need is a Google account and a web browser, and you should be able to replicate what Peter's doing right now. I'll pass it over to Peter so he can share his screen and walk us through the activity.
Okay, thanks, Piro, and thanks, Alex. Now let's get into the actual CodeAlong part of this session. So like Piro had mentioned, we're going to be looking at data points from a data set that looks at images of handwritten numbers. So this is the Google Lab interface, Google Collab. Here we're going to import the data set. And we actually can also look into some of the data sets as well as split it up into training and test data sets. So like Piro had mentioned, 60,000, 10,000 split, and we'll have to run this and we can learn something from it. Okay, so now we see that the X part of the data sets, those actually include the images themselves, whereas the Y parts of the data sets, those include the number that's associated with that image. So now let's see what exactly is in that X data set. We're going to do this through importing matplotlib, and we're going to visualize it as well as look into the actual array of numbers that we're visualizing. Okay, so here we can essentially throw in any number between 0 and 60,000. I'm just throwing in 10. We can see that this is the 28 times 28 graph of a number, and each kind of intersection of these two coordinates represents a pixel. So now let's look at what the computer reads from it. And that is just a bunch of numbers. These numbers represent the shade of color that's in the pixel. So a 0 is white, if you can guess. I believe this first line would correspond with this first line. As you can see, it's all zeros, it's all white here. Then as we get further along, we'll start to see other numbers, such as all the way up to 256, I believe. And that the highest number would be purely black in color. And in the middle, it'll be between light gray and dark gray. So something closer to 0 will be light, something closer to 256 will be darker. Okay, let's move on. We're going to do a couple of transformations in order for, once we get to the point of modeling, for this to be easier for our model to work with. The first transformation we're actually going to do is we're going to flatten the data set. So instead of having these 28 by 28 matrices to work with, we're going to turn them into vectors. Okay, and that simply makes it easier to work with. Not only that, we're also going to condense the data by changing the scale. So instead of multiplying numbers from 0 to 256, we're going to be changing it from 0 to 1. And that will be easier for the computer to work with. Now, this isn't an example of it becoming 0 to 1. This should probably be in the next section, actually. But that's what this code here would have done. Okay, so we would have transformed the data from all these numbers between 0 and 1. So let's look at what the Y section of this data looks like currently. We see that the Y gives us the result. So the first number will equal to 5, the next number is 0, and that's the answer key essentially. Right here, we did X train 10. Okay, so Y train 10 will give us the result of what this number is supposed to equal to, the one that's in the 10th position, or 11th overall position. And that could be 1, 2, 3, 4, 5, 6, 7, maybe 3, I think, if I counted that right. Okay, so let's move on. We're actually, now because we're working with numbers from 0 to 9, you may think that that's kind of a linear relationship, or at least it might be confusing a little bit. But in reality, what we wanted to do is we want to classify these numbers, these pictures that we're seeing over here, and these matrices, which we've converted actually into vectors. We want to be able to convert it into which category does this fit in? Does it fit in a category of what a 0 should look like in this form, or should it fit into the category of what a 1, 2, 3, etc. Right? And to do that, we have to change our data set to be categorical data. Okay, and to do this, we can use a handy method that's named exactly that, toCategory, right? And then after we run that code, we can actually look at what our answer key looks like now. So this transforms our answer key to be 10 spots and a 1 denoting which one is the answer. So does it fit into the category of 0, 1, 2, 3, 4, 5? So the first number fits into the category of 5. And that's also the number we see right here. This was 5, and that transformed into this type of data. So now let's actually use the model. Those models that Piro was discussing earlier, we can actually apply one of them to this data set. And after we've performed all these operations, it becomes slightly faster to run this, although it's still the longest process in this whole data set, in this whole solution of code. And that's simply because we are running it across the training set, which is 60,000 overall observations. And we need to make sure it trains across all of them and it performs the calculations. And once that finishes, which it shouldn't take too long, we can then start to test it and see how our model did. Now, in this case, we are using the decision tree classifier. Is that Piro? I unmuted the mic or no? Okay, I'll keep moving on. So yep, here we have our decision tree classifier. Next, we're going to see how it did. Okay, so here we can really throw in a random number and we'll see what it looks like. And then we can also predict what number it is. So here it's a 3. I think we can tell that it's a 3. And we see that the model predicted it correctly. And this is now on, this means that it's actually predicting these values. So we can actually really throw in any number here and it should show the correct number out here. Not only that, we can now also look into whether it's accurate or not, or how accurate our model actually is. So that's what this line of code here does. And we can see that comparing the results that output, it's actually 87, almost actually 88% accurate. So we've generated quite a good, accurate model. And yeah, that's a quick run through. Go ahead, Piro.
So just a quick summary to summarize. It all looks really neat and nice, but we've done actually a couple of steps here. So the first one is we've actually taken a data set full of 70,000 examples of handwritten values. What we've done is we've only shown the computer 60,000 of those. And the other 10,000 we're calling our test set. The 60,000 is our training set. And what we're doing is we're passing a decision tree classifier this training set of 60,000 values. And what happens is we've taken those values, those are images, and we've converted them into numbers. So that's one of the key things that happens here. We can take any image, and as long as we convert it into a pixel color, so from 0 to 255, we're actually able to create a matrix of all that data. When we flatten it, we scale it, we do all those pre-processing steps, and then we feed it into the model. And what we do is we feed that training set, but we also feed the outcome as well, which is we've labeled as our Y training data. When we feed that into the model, we're saying that if a matrix looks like this, and this is the outcome, then if you ever see that type of matrix again, this is most likely going to be the outcome again. And that's what happens when we try to predict a value. Peter predicted a value, the 2021 value in our data set. But Peter, maybe we can change that to 95 or another value. And let's go ahead and see what that number looks like. These are all handwritten numbers. So we know that that's 0. And when we look at what the model predicted, it's saying that it actually predicted the 0th class. So that first value, it actually predicted correctly. Let's pick another number, Peter. What's another number? Maybe somebody wants to give us a number between 0 and 70,000.
Do you have one?
43284. There we go.
43284? Or no?
Correct.
Okay.
Okay.
Number.
So let's take a look at what that number is. And that number, well, it either looks like a 1 or a 7. So this is where the 88% comes in. What our test data tells us is that out of the 10,000 records that we did not expose to the model, of those 10,000, 88% of those were predicted correctly. In other words, that what the outcome was and what the prediction were matched 88% of the time. And you can kind of see why. So numbers like this, where it's hard to determine whether it's a 7 or if it's a 1, sometimes might throw the computer off. So in our case, the computer predicted that it would be a 7, but in some cases, it might actually be a 1 instead. So there's times where handwritten notes can sometimes be done incorrectly as well. And that's essentially, go ahead, Peter.
So I think it'll take us several attempts if we wanted to try to see it fail, right? Because it's quite accurate. So
that's right. And that's essentially the essence of machine learning. We take some values, some historical values, we train a model based on that historical value. We test the model and score the model to see how accurate it is against the data set that the model hasn't been actually exposed to. And then we use our model to predict if our score is good enough, we'll use that model to predict and hopefully get a value. And hopefully our values are done correctly. So I think that concludes that CodeAlong. What we're going to do now, I noticed that we have a couple of questions here. One of the questions was, can we share the notebook that Peter is working on? So absolutely. Peter, if you want to go ahead and click share in the top right corner and post that link in the Hopin chat. And then it'll be available for everybody. So remember, all you need to use Google Colab is just a Google account, and you'll be able to kind of see it. So Peter, if you want to pop that into the chat, everybody now has access to all this data. Another question that we had here is, what is a tensor? So very, very good question. So a tensor is actually is a multi-dimensional matrix. In its simplest form, it's a matrix that has more than 2 dimensions. So anything 3-dimensional, 4-dimensional, 5-dimensional, and so on. It might be hard to visualize what a 5-dimensional matrix looks like, but computers actually, and the math exists, and computers are able to compute using higher dimensional matrices. So very good question there. Another question is, could you give us some example use cases at work where you would use this type of machine learning techniques? Absolutely. So what you've seen here is actually a really, really good example. So image recognition is a type of machine learning technique that is very, very common, and it's becoming very, very, very important. So a lot of traffic engineers will use computer vision to identify patterns of traffic, traffic flow, and opportunities where traffic could be reduced. And essentially uses the exact same algorithms that we've presented here to identify where is the car in the image, how many cars are there in the image, and then in the next image, how far have those cars traveled, to try to compute velocity, but also number of cars. So working with image recognition. Other use cases, one of the most common use cases that we have is trying to forecast or predict things like sales, predict things like operational impacts to certain things, and all of those use regression type algorithms. We also have fraud detection, which are use cases that we use often with banking and insurance clients, and those are essentially trying to identify, and I'm sure many of you have done this, but you've probably gotten a text or an email from your bank saying we detected some unusual activity. Well, that would be a machine learning model in the back end that identifies abnormal to normal activity. There's a lot of other use cases, such as natural language processing, which powers chatbots, and various other algorithms. But the majority of our ML use cases come from those 5 examples there. Next question, we'll do 2 more. Before you guys have to hop onto the other one. But for production models that you work with, does the training of the model occur only once over the lifetime of the model? Absolutely not. Monitoring the performance of the model happens in a very iterative way. Depending on the size, the breadth, and the depth of the model, retraining could be as often as daily or once a year. But anywhere within that time frame, absolutely. As you notice, the score is starting to decrease. A change in some of the underlying environment, a retraining of the model is absolutely required. Okay, last question we'll take. How many iterations would you go through to optimize your model? Depending on how much data is available to us, keeping in mind that every time we train the model, Peter's very, very simple model with only 70,000 data points took about 30 seconds on a very, very powerful computer that Google has provided to us for free. But generally, when we have larger data sets, you're very constrained by the amount of time that you have. So ideally, you want to keep your iterations to a minimum, but ultimately, you're going to have to require maybe 4 or 5 iterations to essentially optimize your model, tune your parameters correctly, and then ultimately just identify anything that's unexplainable within your model, and hopefully either try to remove it or to try to add additional inputs and features to account for those. So very good questions all around. We recognize that we're 1 minute over time. Thank you for joining us. Peter has already posted the Collab notebook link on the chat here. Feel free to check it out and play with it yourself and copy it, download it over into your Collab environment. I'd like to say take care, everybody. Have a great weekend. I'll pass it over to Alex and Peter for closing.
No, so I think you covered everything, Piro. So thank you everyone for joining us today, and hope you have a great rest of the conference. And if you're interested in know anything further, feel free to ping Piro, myself, or Peter, and we'll be happy to answer any other questions you might have offline. Thank you, everyone.
Thanks, guys.
Take care, everyone.